Hiya! So in this video, we're going to look at the second case in particular. So here we're going to have when things are reflections. So here, let's kind of go back and kind of recall some of the things. So here we're saying k is odd. In other words, k is equal to 2m minus 1. And if you kind of remember, what this is basically saying is my psi is equal to phi minus pi over 2 plus 2m pi. And the matrix we were using to kind of remind ourselves was the matrix of cosine of phi, sine of phi, cosine of psi, sine of psi. So just like with rotations, what we're going to want to do is change these into some other, into phi, change the size into phi's to have just one variable. So we do a same game. So we take psi here, cosine of psi, we plug in what our psi is. The 2m pi we don't really need, right? Because it's just going to keep us in the same loop. So we just have cosine of phi minus pi over 2. Well, this is just the same thing as sine of phi. And in a similar line, sine of psi is just minus cosine of phi. So what this gives us is I can define some linear operator. So here we'll denote it by q of phi instead of, so p was taken, so we'll do q of phi instead, pq. And this gives us the operator cosine of phi, sine of phi, sine of phi minus cosine of phi. And where is these coming from? Sine of phi is really just cosine of psi. And cosine of phi, this was just a sine of psi. Okay, so we have this equality. And just like last time, what we're going to do is we're going to take an arbitrary vector and multiply. So we take some arbitrary vector here. This time it went over a line. I don't know why, but that's life. And we're going to multiply these together. So let's do that. Sine of x1, x2. And so we're left with x1 cosine of phi plus x2 sine of phi, x1 sine of phi plus minus x2 cosine phi. And then therefore putting the linear operator on this vector, what we end up getting is we already have these, so we just have to put in our basis, right? And that gives us this relation. Now, in this case, what's the determinant? So let's look at this determinant. This is minus cosine squared phi minus sine squared phi. I can pull out a minus sign in front. Cosine squared phi plus sine squared phi. In other words, this is equal to minus 1. So this determinant is equal to minus 1. So q does not. So the key point here is that q prime does not preserve orientation. So in fact, it'll swap the orientation. So let's look at a small example. So if I let phi just be the following. So we saw that P of phi is preserving the orientation, but Q of phi is not. So how do the two kind of relate? So in order to relate the two, we're actually going to introduce a third linear operator. Here we're going to call it R. And we're going to define it in the following way. So basically R of E1 is E1, R of E2 is E2. So in other words, R of B is 1, 0, 0, minus 1. Okay? Now R is going to be the reflection. So here we're going to say it's the reflection that sends E2 to minus E2. So you can kind of see E1 stays where it is and we don't change E1, but E2 we flip to the opposite side. Another way of saying this, it's the reflection in the line spanned by E1. Now, if we recall from the previous example, so 1.66, this was saying that it does not preserve the orientation. And what we have is if we actually compose P and R, this is just Q. So we can kind of see this in the following example. So Q is this matrix that we had from before. This is the P, and this is the R that we just defined. So another Q is a rotation times this kind of reflection over E2. So we're going to go into this a little more further in the next video when we look at an example. But for now, we're kind of just going to leave it as is. But the main key point here is that Q is the composition of a rotation and a reflection. So I will see you in the next video where we look at an example of a Q, and in particular, look at how this relates to reflections. So I will see you then. Peace.